Hi everyone, my name is Vinicius Lamas von Sosten and I will present the work Oblique Shock Wave for Air at High Temperature. First, what is a scramjet? Scramjet is a fully integrated, air-breathing aeronautical engine with no moving parts that uses the oblique shock waves generated during the hypersonic flight based on supersonic combustion. So, the main components of the scramjet are the inlet, the compression section, the combustor, and the outlet, the expansion section. We are going to look principally to the inlet section because it is where the oblique shock wave appears. So due to the high speed, the temperature promoted by the oblique shock wave caused by the scramjet is also quite high, causing chemical reactions in the gas. So this high temperature air is what occurs in the real gas that we call air in thermodynamic equilibrium, that will cause reactions such as dissociation of the oxygen at 2000 kelvins and nitrogen at 4000 kelvins, or formation of nitrogen oxide at 6000 kelvins, and even ionization at higher temperatures as 9000 kelvins. So for the real gas, the air in thermodynamic equilibrium, we need to use the method present in Tannehill and Milde that use the polynomial correlation and tabulated and calculated coefficients that we will present in this work the modified algorithm to solve this problem. And for perfect gas, we use the analytical method described in Anderson. For the oblique shock wave theory, we need to assume that it will be a steady and adiabatic flow with no viscous effect. Then we will get from the continuity equation this first equation, the second equation we get from the momentum equation, and this last one from the energy equation with the entropy equation. Notice that the index 1 is for before the shockwave and index 2 for after the shockwave. Notice that we will only use the normal velocity to the calculations, not the tangential one, because it does not affect at all. And beta stands for the oblique shock wave angle and theta for the flow deflection angle. So the oblique shock wave relationships for calorically perfect gas come from the manipulation of the previous equations using the speed of sound. Then we get these relationships that is only in function of the Mach number. So we have the pressure ratio, density ratio, temperature ratio, relation between theta and beta. And for air in thermodynamic equilibrium is a little bit more complex because the specific heat ratio is no longer constant. It's a function of the pressure and the density. And these constants C and D we can found in the work of Tannehill and Milde. So the algorithm for numeric solution of the previous equations is this. First, arbitrate a value for the normal velocity ratio. A value of 0.1 is good. Second, using secant method, obtain a value for beta for a given theta using equation 21. Third, arbitrate a value for density ratio. A value of 0.1 is good. Fourth, with the calculated values of pressure 2 and enthalpy 2, calculate the specific heat ratio from equation 14. Fifth, calculate density 2 from equation 13 to obtain a new value for the density ratio. Sixth, use the new value of the density ratio to obtain new values for the pressure 2 and enthalpy 2. Then repeat the steps 4 to 6 until convergence is achieved. That is, until the value of the density ratio between two consecutive iterations is practically equal. Seventh, calculate the new value of normal velocity 2 from equation 18 using the new density ratio. Eighth, with the new value of the normal velocity ratio, use the secant method to obtain a new value for beta using equation 21. Then repeat steps 3 to 8 until convergence is achieved. That is, until the value of beta between two consecutive iterations is practically equal. So we have the iterations 4 to 6 inside the iterations of steps 3 to 8. So we have an iteration inside of another iteration. So when convergence is achieved, after all this, we can finish with the correct values of beta, normal velocity 2, density 2, pressure 2, and enthalpy 2. Calculate now the temperature 2 from equation 16 and velocity 2. Now we have all the parameters we need. So to validate this algorithm, we use the input values of presented by Moura and Pinheiro Rosa and compare the results with the work of Moura and Pinheiro Rosa and Nagamatsu et al. And our present results are here. So we can see that is a close result to their work. So now that's validated, we can apply our code. First, we need the thermodynamic atmospheric properties at 30 kilometers altitude. Then we can have this flow deflection angle versus shock angle graphic. That is the dashed lines shows the calorically perfect gas, and the full line shows the air in equilibrium. So we can see that for higher velocities and the same flow deflection angle, we get lower shock angles for air in equilibrium. And then we get the numerical results for Mach 7 and 10, and for theta 20 degrees and 30 degrees. We get the pressure ratio, temperature ratio, and beta. We see that they get lower than in the air in equilibrium compared to the calorically perfect gas. And here you get the final results for pressure, temperature after the shock wave for Mach number 710 and for theta values of 20 degrees and 30 degrees. We can see too that the pressure and the temperature are lower for our air in thermodynamic equilibrium. So to conclude, results demonstrate that ideal gas considerations lead to a stronger shock wave than equilibrium air. This is because energy is not absorbed by molecular phenomena, not considered on the analysis. These errors are conservative and provided a sufficiently approach to preliminary design of aerospace vehicle based on supersonic combustion propulsion system done under calorically perfect gas behavior. I would like to thank to the Universidade Federal do Rio Grande do Norte, Universidade do Vale da Paraíba, and CAPES. Thank you all for watching.